Hi dear students, now we see about shape independent effective range theory of NP scattering. In this NP scattering, it is neutron and proton scattering. Okay, the scattering value is fully independent of shape. Okay, now we have considered the scattering length, that is denoted as A, which is equal to some parameters, that is minus delta divided by Q. Here delta is represents the phase shift and K is the wave vector. Then it is and then scattering is also in the produce the S wave. So these are the have measured use the square potential. So the phase shift delta is measured accurately by using the phase shift method as well as general theory method. But in our case, the general theory method is very accurate compared to phase shift method. So we have use the general theory method instead of phase shift method. And then effective range. What is mean by effective range? It is defined by the term the scattering at low energy in terms of the range over which the potential is especially effective, because the scattering is only occurred in the one particular range. That particular range, the potential is very high. That particular range is called as the scattering length, and then the range is very effective, so this range is called effective range, and then the range is simply denoted as the dimension of length. So we have denoted as the dimension of length. Then this theory is the scattering, so automatically it is shape independent, so it is the denote in the F shape independent effective range theory. Here the scattering is occurred means automatically it has some wave functions is also produced. We have considered two radial wave functions, one is U1 and U2, and then corresponding energy scattering energies also, they are E1 and E2 respectively. So automatically we have to write this Schrödinger equation using these two wave functions and energies pair. So it is d square u1 by dr square plus m by h cross square e1 minus v into u1 is equal to 0. In the similar equation, it is u1 is replaced by u2 and e1 is replaced by e2 is the second equation. Okay, now here in this equation m is denoted as the mass of the particle, and here we have used the NP scattering. Both neutron and proton almost have the relative mass, because they are slightly changes the mass, but in this case we have used the reduced mass. Okay, that is denoted as m, and v is the nuclear potential of any shape of the nucleus. Okay, because nucleus is not only the spherical shape, it is maybe prolate, oblate or triaxial or any other shape. So in this case we have used the potential, it is the common potential for this all the shape of the nucleus. Now we have used the another formula. That means in our case we have the first equation is multiplied by u2 and second equation is multiplied by u1. So automatically the entire equation, first equation is multiplied by u2 and it is denoted as equation number 3, and similarly the second equation is multiplied by u1 and it is denoted as equation number 4. Further, now the equation, both the equations are subtracted. That means equation number 4 minus equation number 3. So automatically the equation number that is here 4 minus equation number 3. In this case the equation number 4 d squared u2 divided by dr square, that means it is double differentiation of u2, so it is denoted as u2 double prime. In the similar way, in the first equation, that is equation number 3 also, d squared u1 divided by dr square, it is also denoted by u1 double prime. Okay, now the entire terms are included and cancel the terms and remaining terms are there. Okay, so in our case we have consider, that is m by h cross squared into E1 is denoted as K1 squared, and similar way E2 into m by h cross squared is K2 squared. So these are the substituted in the above previous equation and we get this equation. So integrating on both sides, automatically this U2 double prime is replaced by U2 prime and U1 double prime is replaced by U1 prime. So in the limit from 0 to infinity, here is also K1 and K2 both are the constants, so taken outside, simply U1 U2 into dr, it is limit is also substituted. So here we have considered another one new wave function for our convenience. So it is V and it is identical with U. So it is only used for the outside potential well, because in the inside the potential well you have used the wave function that is U. In the outside potential we have used the wave function, it is V. So it is extrapolates. It is denoted in the this diagram is also. Suppose we draw the diagram for the radial function as well as the distance length, scattering length means automatically the wave function is like bending is like that. It is the radial wave function and it is for the effective range theory. Here in the inside it is we have used the potential, I mean vector is wave function is U and then outside it is denoted as V. So the outside wave vector becomes 0. So becomes the wave vector value is 0 at the U is equal to wave function U is equal to fully 0 at R is equal to 0, but the value of V is maximum 1 because it's reached the maximum value. The wave function is denoted by the equation number 7, that is sin kr plus delta divided by sin delta. Now we have used another one, that is this value is used and write the equation which is similar to the equation number 6. Here U1 and U2 is replaced by V1 and V2 and V1 V2 prime, these are the used, and then subtract these two equations and we get the answer. First of all, we substitute the upper and lower limit. This is for the upper limit minus lower limit, which is subtracted by this subtracted this equation by this equation. So automatically here the upper limit and minus lower limit, and then your right hand side is also we have taken k1 square minus k2 square is the common one, so taken outside, simply integral of 0 to infinity v1 v2 minus u1 u2 into dr. Okay, now we have considered the outside potential U1 is equal to V1 and U2 is equal to V2. At the same time, at R is equal to 0, automatically U1, U2 is equal to 0, because in the value of R is equal to 0, there is only V is present, there is no U, so automatically U1, U2 is equal to 0. So these values are substituted in this above equation, so automatically the terms, these are the common term and then it is cancelled. At the same time, this term is also equal to 0 because U1 and U2 is equal to 0, so the remaining term is there. So which is equal to, that is minus of V1 V2 prime minus V2 V1 prime is equal to K1 square minus K2 square the whole square into integral of 0 to infinity V1 V2 minus V1 V2 into dr. Okay. Already we know the value of V, that is sin kr minus plus delta divided by sin delta. So in our case we have used V1 V2 using that equation, and V1 is replaced by k represented by sin k1 r plus delta 1 into sin delta 1. V2 means automatically k is k2, delta 1 is replaced by delta 2, automatically we get this equation, and then it is differentiated so with respect to r. So automatically V1 prime and V2 prime or get this equation. From this equation, sin is differentiated means cos, and then k1r is differentiated, we get the k1 and then divided by sin delta 1. So these are the common term, I mean constant term, so these are the same. Now we have consider at the value of r is equal to 0, automatically in this above 4 equation the r term is equal to 0 means it is simply sin delta 1. So sin delta 1 divided by sin delta 1 is equal to 1. Similarly in v2 is also equal to 1, but in v1 prime and v2 prime we get some another one equation, that is k1 cot delta 1 and k2 cot delta 2. So this is denoted by the equation number 11. So these values are substituted in the previous integration equation. So this is your previous integration equation. So the values are substituted in this equation and we get the term this term. So first we have consider k1 is represented as simply k for the energy and k2 value. The k value is 0 energy for k2. So now we have consider v1 is equal to v and u2 is equal to u0, means automatically the values are substituted in this above equation. So from this scattering length, the k naught cot delta naught is equal to minus 1 by a. It is the first term in our equation. So v naught is equal to, that means our general formula v naught is equal to at limit k naught tends to 0 means sin k naught r plus delta naught divided by sin delta naught. So the values are substituted in this equation, we get simply a minus r divided by a, which is equal to 1 minus r by a. So from this equation we have considered the integration term in this equation is simply denoted as rho, and it is 2 into this integration. So automatically in your integration it is simply rho divided by 2. So these values are substitute in the above equation, that is your equation. Okay, so here we have considered this term is moved to other side, and so it is denoted as here, and it is simply denoted as k1 k cot delta 1 is denoted as k naught cot delta naught. Okay, so k naught cot delta naught means automatically minus a plus k squared 1 by half rho of 0 e. Here 0 is eliminated, simply denoted as rho of e. So in this equation can be written in this form. Here v into v naught minus u into u naught, because u1 u2 v1 v2 is replaced by v and v naught. So in our case it is simply denoted as v naught square minus u naught square. So it is r naught or r effective, that means effective range. Okay, so from this equation we get the formula k cot delta is equal to minus 1 by a plus half r naught k square. So we have now calculate the scattering value, that is S-wave scattering cross section, that is for the NP scattering. So it is general formula 4 pi k squared cosecant square delta. So these values are substituted by using this rough work. So 4 pi k square cosecant square delta means it is 4 pi k square. Cosecant square is replaced by 1 plus cot square delta. So cot square delta means it is k squared is multiplied in the inside of this bracket. So automatically k squared plus k squared cot square delta. Already we know that k cot delta value, this is in the previous. So here we have it is a square term, so the minus is inside. It is multiplied with 1 minus sign, so automatically it is a first term and minus this 1 into second term. So this is in the your equation, and so now automatically it is in the square term. So here we have generally this value is directly substituted in this equation. Okay, so in this equation we get the use the LCM term. So the equation is a square k square plus half r naught k square into a plus minus 1 the whole divided by a square. So this is our equation. This is our general final equation for the scattering wave. But in our radial function we have used two types of wave functions. One is u of r, another one is the v of r. U of r is only used for the inside the potential well, and then it is only for the external region r is less than r is less than b, and v of r is it is extends function normalized by using unity at r is equal to 0. So only it is used for at r is equal to 0. So these two wave functions are represented like c into e power minus alpha r and v of r into e power minus alpha r at r is greater than b. Here C is represents the constant value. Already we know that in our equation alpha is the mb divided by h cross square the whole power half. So these values are substituted in the previous equation which is similar to this equation. So we get the value of integration is denoted as simply 2 divided by alpha squared 1 by at minus 2 divided by alpha. So we have experimentally we have calculated some values. These values of alpha, S, alpha, T are substituted in the above equation and get the scattering cross section. We have finally get two terms, one for the triplet state, another one is for the singlet state. Triplet state is 3/4 of the triplet state and 1/4 is singlet state. So the values are substituted in the equation. Finally we get the scattering cross section for the NP scattering. It is fully shape independent. There is no shape is involved in the scattering range or wavelength or any other parameters. Only it is independent of the shape. It is the main task for the effective range theory of NP scattering. Okay, thank you.